A batter hits a baseball pitch with an incoming velocity of negative 40 meters per second in the x direction, 0 meters per second in the y direction. The hit exerts a force of 17,000 newtons in the x direction and 4,800 newtons in the y direction over a period of 0.7 milliseconds on the 150-gram baseball. If the position of the ball when it is hit is 1.2 meters above home plate and the fence is 120 meters away and 4 meters high, is the hit a home run? We will start by drawing a picture and defining our axes such that the positive x-axis points to the right and the positive y points up. The distance from home plate to the fence will be labeled D and the height of the fence labeled H. In order to approach the problem, we will divide it into 3 parts. The first event will be denoted by the beginning of the hit, the instant before the baseball connects with the bat. The second event will be the end of the hit, or the instant right after the baseball leaves the bat. And the third event will be when the ball reaches the fence. We will now list our knowns and unknowns. We start with the mass of the baseball, which is 150 grams. We can convert this to standard units by multiplying by 1 kilogram over 1,000 grams, which gives us a mass of 0.150 kilograms. The velocity of the baseball before it connects with the bat is labeled V1 and is given by negative 40 meters per second in the x direction and 0 meters per second in the y direction. The force of the hit is 17,000 newtons in the x direction and 4,800 newtons in the y direction. The duration of the hit is denoted by delta TH and is given by 0.7 milliseconds, which we can convert to standard units once again by multiplying by 1 second over 1,000 milliseconds, giving us 0.0007 seconds. The distance from home plate to the fence is 120 meters and the height of the fence is 4.0 meters. The unknown quantities that we want to find are the velocity of the baseball after it leaves the bat, marked V2, the duration of the baseball's flight, marked delta TF, and the height of the baseball when it reaches the fence, Y3. We will start by finding V2 using the momentum principle. In this case, we are assuming that over the course of the hit, the force of gravity is negligible and the duration of the hit is short enough such that the change in position of the ball over this time is negligible compared to the change in the position of the ball over the rest of its flight. We can express the momentum principle as the force of the hit is equal to the change in momentum of the ball over the duration of the hit. We will start by multiplying both sides by delta TH, giving us delta P equals force of the hit times delta TH. We will then split delta P into the final momentum minus the initial momentum, P2 minus P1. We can then bring P1 over to the other side, giving us an expression for P2. Dividing both sides by the mass, m, then gives us an expression for the final velocity vector in terms of the initial velocity, V1, the force of the hit, the duration of the hit, and the mass of the baseball. We will now find the duration of the baseball's flight, delta TF. We are assuming that there are no forces in the x direction acting on the baseball, including no force of air resistance, which means that the x velocity will be constant over the baseball's flight. We can thus say that the velocity in the x direction is equal to the change in the x position over the change in time. We can multiply both sides by delta TF to give us delta TF times V2x equals delta XF. We can then divide both sides by the velocity to give us an expression for delta TF in terms of the change in x position and the velocity. We will now find Y3, the height of the baseball when it reaches the fence. To find this quantity, we will use the derivation of the change in position from the momentum principle under constant force. For more details on this derivation, see page 61 of the 4th edition of Matter and Interactions. From this derivation, we can use the result that y3 equals y2 plus v2y times delta tf plus the force in the y direction over 2 times the mass of the object times delta tf squared. In order to solve this equation, we must leverage our previous results to find v2y and delta tf. We know that the velocity vector at event 2 is given by velocity 1 plus the force of the hit times the duration of the hit over the mass of the baseball. Take a moment to pause the video and try and solve for this quantity yourself. Plugging in these numbers and calculating gives us the result that the velocity 2 vector is 39.3 meters per second in the x direction and 22.4 meters per second in the y direction. We will now do a quick unit check of our result. We know that velocity 2 will have units of meters per second, velocity 1 has units of meters per second as well, and force has units of newtons, time has units of seconds, and mass has units of kilograms. Splitting the newtons into its component units of kilogram meters per second squared, we can see that the kilograms will cancel and one of the seconds will cancel, leaving us with meters per second plus meters per second as we desire. We found that delta TF is given by the change in the x position of the baseball over its flight divided by the x component of the velocity. Thus, we have 120 meters over 39.3 meters per second, which gives us a flight duration of 3.05 seconds. Over the course of its flight, the only force acting on the baseball is the force of gravity, which acts in the y direction alone. This force is given by mg, where the m is the mass of the baseball and g is the acceleration due to gravity. This force must act in the negative y direction as we have defined our axes. Calculating it, we find that it has a magnitude of negative 1.47 newtons. Now that we know all these components, we can solve for y3. Take a moment to pause the video and do this on your own. We find that the height of the baseball when it reaches the fence is 24 meters, which is greater than the height of the fence. Thus, the hit is a home run. Now we must check our answer. For our units check, we know that y3 will be in units of meters, y2 in units of meters, v2y in units of meters per second, and delta t in units of seconds. The force on the baseball is in units of newtons, delta t squared gives units of seconds squared, and the mass of the baseball has units of kilograms. Once again, we can split the newton into kilogram meters per second squared, and we see that both the seconds cancel and the kilograms cancel. This leaves us with an addition of meters, which checks out. For the ball to fly this far above the fence, it must have been a very strong hit. However, this order of magnitude is still reasonable and thus checks out.